So next up is our first
Does this work?
Real panel discussion. Should we wait for more data and uncertainty in contrail prediction and climate impact, or can we learn to deal with the uncertainty? And we talked about this early on here in the presentation, that this is where a lot of the conversations normally end. It's too uncertain, let's wait, let's have some more data, but maybe there is a way to start doing something now. To moderate this discussion is Vincent de Haes. He's a senior sustainability aviation consultant in 270 with expertise on future fuels in aviation, sustainable airports, and carbon, as well as non-CO2 emissions. His goal is to ensure the aviation sector can achieve its environmental license to operate. And with that, over to you. Thank you.
Thanks, Joachim. Okay, I hope this doesn't look too weird. I'm the first one to try it on, I think. But I'm glad that we can have the first panel discussion, and that we can also have a bit of interaction on this very interesting topic that we've had an introduction on already. And I'm very glad to do that with these four great people, all experts in their field. And I'll give a short introduction. Then we'll go ahead to some questions we prepared in the discussion. In that discussion and in the preparation, I personally learned a lot again, so I'm hoping that everyone here will as well. And then we'll also make sure that there's sufficient time for questions from the audience so that we can discuss this topic in more detail, and that you can also pose some of the questions you might have on uncertainty or certainty in contrail prediction and monitoring. So first, Marc Stettler, professor at Imperial College, introduced himself sufficiently, I think, but does a lot of work on everything with contrails. Next, Paul Hodgson from the Aviation Impact Accelerator Institute, director there, and leading the 5-year plan, which puts contrail mitigation as one of the, if not the first priority of actions to take. Then Carlos López de la Osa from Transport and Environment, leading the contrail work there, and really providing some insight on communicating about uncertainties. And finally, Sebnem Erzan from Google, leading the team on sustainability, flights, transport, and travel sustainability. I'm saying that correctly? Great. And working on the travel impact model, contrail validation, and a lot of other projects with the sector. So that's great to have them here. Starting with the first question, and I think that's a bit of context setting. What are contrail uncertainties right now? And can you maybe also give some definitions as we go along there?
Thanks, Vincent. And obviously, we've heard a lot already about some of the large uncertainties, but we thought it'd be helpful to try and break down some of the different types of uncertainties and definitions. So this diagram is going to try and help us a little bit. So to begin with, we have all the contrails on the world and the warming that they cause. Now, we've heard there's a reasonable amount of uncertainty about this. It's actually a truly unknowable number because, as we'll see, we actually cannot physically measure all this directly. And we know the uncertainty at the moment on this is in the order of maybe plus or minus 70%, different debates about how much. Within that, we have what we might call the observable contrails. These are contrails we can effectively see from satellites or ground detection systems, and we can then use models on top of that, which also have uncertainty to add up what we think the contrail warming is, or what the total contrail is from all the contrails that we can actually observe. And within this category, then we have the contrails that we can actually attribute to an individual flight. And that tends to be a smaller number than the other numbers because there's missing flight data from systems, or sometimes we can't see the connection between the flight and the contrail that we then see on a satellite image. Perhaps the flight went through a long time before and the wind has advected the contrail. Obviously, more and more work on models and detection systems tends to try and improve this, but currently not all contrails can be attributed to an individual flight level. And so counterintuitively, generally the uncertainty is higher at an individual flight level than it is on the global average, which is sometimes counterintuitive. It's a little bit like saying the average height of a population is more certain than a model for the height of any individual within that population. Now, that's effectively what the warming of contrails are, and we often refer to this to a degree as scientific uncertainty. And what happens when we then try and make predictions or even just measurements of live contrails? And so the red circle here shows a made-up example of some predictions of contrails. And this is going to form three regions that we're going to use to talk about how good predictions are. It turns out one of the reasons engineers find it difficult to talk about how accurate, say, prediction systems are is it's quite difficult to boil down to a kind of single number, as we'll see. And so you can see that we have three zones here. We have our green zone, which is what effectively our false negatives are. These are the contrails that we failed to predict. We could call those our missed opportunities. So if we were to implement these predictions into an avoidance system, we wouldn't manage to avoid the ones that are currently in green. The ones that are still just in red are what I like to call ghosts. So these are our false positives. These are predictions that we made that were contrail-forming regions, but actually turned out there was, in fact, no contrail there. It was a spectre, an illusion of a contrail that was there. And finally, in the middle, we have what we might say as our true positives, the ones that are our successful hit rates. Now, there are two metrics that we use to define this. Now, these metrics are something we use in detection systems or prediction systems, not just in contrails, but in medical systems, like from contrail detection to pregnancy tests. And this is recall and precision. So recall is the proportion of the contrails that really exist that we successfully predicted. And so it's the hashed region over the total green region. So this is effectively how much contrail reduction we achieve if we successfully manage to implement all of our predictions. And our precision of our prediction systems is, of the predictions we made, how many of them were real and as opposed to just ghosts. One of the challenges in these systems is these two things are interchangeable. There's a trade-off between these two that we can make depending on how much we want to prioritize one versus the other, which is ultimately a policy uncertainty. So in medical systems, you'll tend to see for diagnostic tests that we will favor recall over precision. And the reason for that is if you're trying to detect for Alzheimer's, say, you want to make sure you catch everyone that has Alzheimer's, even if that comes at a penalty of picking up some people that actually don't have Alzheimer's, because you then take action with those. So if you wanted to, if from a policy perspective, you wanted to prioritize contrail avoidance to an extreme, you would prioritize recall.
Paul, just making that in the visual, that means that you're making that smaller circle larger. Is that a correct?
Yes, so we can literally do this. Thank you, Vincent. So yes, if we made a lot more predictions, what you can see is we get a much bigger proportion of the green, but at the penalty of many more ghosts. And the penalty for more ghosts is we have to spend more, we have to take more action regardless of whether it's contrail or a different system. So this is a policy uncertainty to a degree. We can actually tune systems. Now, the better we make prediction systems, the better both precision and recall get, so the kind of less horrific the trade-off becomes. And to illustrate this a little, we have a game of battleships, but with imperfect data. So we can see here this, I don't know how common the game of battleships is these days, but effectively we have to guess where our opponent are, and we're guessing where ISR regions are. But data is always uncertain, so we've got a slightly grainy image here. And so we might, for instance, decide that we're going to make these 10 predictions because we're going to have a very low cutoff for our threshold. We want to be very confident. And if we then look at what the real image was, we can see that in this case, our precision was about 90%. 90% of our predictions were correct, but we missed 3 of the contrails, right? So our recall was only 75%. Instead, if you were to make many, many more predictions, you could shift your recall up to 92%, but at the penalty of a lower recall.
Lower precision.
Sorry. This is why it's confusing. And so the final thing we need to note on uncertainty of these, as well as the uncertainty of the actual detection systems, we then have the operational or engineering uncertainty. So not all of these red zones we may have actually in practice been able to avoid, even if we had predicted them. I know Christoph and Adam have talked earlier about some of the reasons why, in some cases, due to congestion or due to a lot of other factors, we may not actually be able to avoid those regions, and that creates quite an uncertainty on operations. The final thing I'd like to note, and I know Adam actually touched on this earlier, is about the uncertainty on lots of predictions tends to be that the contrail forming region is drifted slightly from where it really is. And that can mean that some of these numbers can be misleading, because you might say, well, if this black zone is actually reasonably near the other black zone, then we might find that we would have avoided it anyway. And so the fact that we didn't predict it may have not mattered, because we don't fly the routes hugging the contrail forming regions, not least because we can only fly at distinct flight levels. And so depending on whether you assess these metrics on a point-wise basis or on a practical avoidance basis, shifts some of these answers.
Thanks. I think that's a good first introduction, and the visualization really helps. I think also it's good that if we go down a bit further in those uncertainties, you've got the data, so the black and the gray squares, and the models which predict where those contrails will form, and you can look at the uncertainties there. But we also discussed the fact that there's uncertainties at levels below that, whether that's maybe the political side, the policy, how do you form policy, and how do you choose metrics in that, but also to what trade-offs you want to go to, and the uncertainties in engineering, so how you are able to actually achieve some of the contrail avoidance that you want to get. And maybe Marc, you can provide a bit more thought on to what level those uncertainties are important and how they function.
So when we've done analyses of contrail formation from flights globally, and we've done sensitivity tests and uncertainty analysis, clearly there's uncertainty at all of the levels of the model, right? And all of the inputs that you put into a model. We've certainly kind of identified that there is significant weather uncertainty, and that's probably, at this moment in time, the largest uncertainty in terms of quantifying global radiator forcing from flights, but also what the contrail effect of a particular flight was. As Paul said, there are things you can do to deal with that uncertainty. So one of the things with the weather data and weather forecasts is that there are limited observations, and if we take the observations at cruise altitude of ice supersaturated regions, we know that we see a slightly different distribution in the model compared to what the observations are. So on average, you could correct for that, but clearly that is not going to solve your problem for a specific flight. So better understanding of the mechanisms by which ice supersaturated regions are forming, and that's an active area of research, I'm sure, from not just from meteorologists, but also people who use meteorological data. So I think that that's one of the things, but I am optimistic in terms of the potential for improvement. Certainly, also making confidence predictions. So are you more or less confident that a prediction is going to be accurate or not? In specific types of weather conditions, it might be possible to be more confident than in others because you have a better understanding of the mechanisms and processes. And then as we are able to assimilate data into weather forecasting, that improves. As with anything, I think it's important to recognize we're talking about uncertainty here with respect to contrails, but there's uncertainty even in the CO2 values that we would also estimate from our global studies, right? So there's uncertainty. We don't know fully the aircraft mass, for instance, so that leads to an uncertainty in our estimates of CO2 and fuel consumption for a flight. so I just make that point that there's uncertainty in lots of these areas that affect CO2 as well as affecting contrail estimates.
And then because in the opening presentation, you also discussed the different metrics that are being applied, and that's a choice, that choice leads to a different trade-off potentially. Would you classify that as an uncertainty, or is that the wrong way to look at it?
Well, there is uncertainty in those metrics as well. So there will be an uncertainty in the global temperature potential or global warming potential of any one of those, or any greenhouse gas. But yes, there is a choice, right? There is a choice as to are we more concerned with integrated radiator forcing or a temperature change? Yeah, it's a choice we have to make. Ultimately, I don't think it really changes the way that we at a high level look at the problem.
Mm-hmm.
Contrails are still important. And I was referenced earlier as well that a paper by Audrey and Barella, which is that actually the metric that you use doesn't really affect your decision to deviate a flight or not, because the upside, the benefit is so large to reducing contrails, and the penalty of the additional fuel burn is so small.
Yeah, great. Then maybe going to how do we transition from that uncertainty and understand this uncertainty to application and to providing information not only to stakeholders but also to the wider audiences, as Google is trying to do in the travel impact model. And maybe, Sebnem, you could share a bit more information on how you've been able to do that and progress in that, I believe, over the last few years.
Happy to. So when it comes to the uncertainty and how we can communicate it, so we think about it in two folds, right? One of them is like we have a model where we are providing contrail formation areas. It's a prediction to the industry so that it enables the stakeholders, the industry, to reroute the flights. So that's one piece of it. The other is like how do we communicate to the broader audience so that everyone understands like what's there. So we all acknowledge the uncertainty. So, however, we have this collective hope that we can be more ambitious about this contrail opportunity because we still believe, like scientifically, like there's a huge opportunity even under the big uncertainty. So, when it comes to the models, so our model is not a definitive model. It's not a yes and no. So it's a probability. So that's why we, of course, like include and take into account the uncertainties in the model. So I think what's important here to make this obvious to the stakeholders so that like it's transparent and clear for them. So when they're making the decision, so they know it's a probabilistic model. And of course, research is going on. We are all collaborating on the research side. How can we address those uncertainties and have better predictions in the future? So that's the first part of it. And when we are doing this contrail formation area predictions, of course, we are using weather data, we are using satellite imagery, we are using the flight paths, and of course, because the data is so huge, we apply AI, and then we have the contrail prediction areas. So this is one part of it. The second part of it is also the communication to the audience. So we have this travel impact model where we are showing the CO2 emissions on our own platform on Google Flights, but many partners are using that too, like Booking, Expedia. So whenever you go, it's like a lot of the partners, like a lot of the OTAs or platforms that you use to book a flight, use the same number, the travel impact model number, where we are estimating the CO2 emissions. So at the beginning of our journey, so we had this blanket number where we were also putting for a multiplier for contrails, but that's not the best way to reflect it in our own purpose, because in the travel impact model, we are estimating a CO2 emission per flight. So that's why for the time being, we are not showing any contrails numbers. But we have this travel impact model advisory committee where we are working towards how can we show the higher probability of contrails for that specific flight and make it aware for the users to understand it. Because for the time being, we don't feel comfortable putting a number together with CO2, merging them too, but there should be a way to show it. So we are working towards that. We made a great progress. but still we have a bit of work to do, but we are testing some ideas how we can make it meaningful for the users so that they also understand like what's the impact of their flight, both on the CO2 perspective, but also on the contrails perspective.
Thanks. Clear, and we might get a bit further into that later on. Now, just kind of going to a question for you, Carlos. If I give you 1,000 flights to analyze, and I ask you what's your hit rate, if we're going back to the graph shown by Paul, can you tell me that within what range, just so we make it practical and what kind of an airline might see when they ask this question?
Yeah, well, that's a really good question that at TNE we asked ourselves a few months ago, and the conclusion is no. Sorry, we can't give you an answer today, a definitive answer. But that's precisely why we developed a sort of shore sensitivity analysis to understand, okay, we can't predict today what the hit rate would be. Also, there's some uncertainty on the feasibility of carrying out the contrail avoidance maneuvers and how much fuel are we going to be consuming. So that's really why we built that chart there with two axes. On the x-axis, you have the hit rate. And on the y-axis, you have the fuel consumption, the fuel burn penalty. Obviously, you want to be as high and to the right as possible, but we found that for the most warming contrails, those famous big hits, which make up 80% of contrail warming, even if you are at a 10% hit rate, which is really, really low, and you're burning a 5% more fuel, over a 100-year period, the climate outcome is still beneficial. And if you go to the upper right, we're talking about hundreds of times more, or as Christoph showed before, even 1,000 times more. If I remember correctly, it was 15,000 tons of CO2e at a penalty of 50 tons of CO2. So we're at 300, kind of. But that really proves that if we focus on the most warming contrails, doesn't matter exactly where we land at the moment, and we're keeping improving it every day. But even if we land somewhere in the middle, which is what today we're seeing we can get to, it's really a no-brainer. And of course, we're working to improve it day by day. And then, as well, to build on the metric question, we're using GWP 100 here. If we looked at GWP 20, the benefits would be higher. And if we used other climate metrics, the outcome will also be probably the same. It's still beneficial.
Paul, I'll give you the phone 1 sec. Maybe just, and we didn't prepare this, so I might look silly asking this question, but the top right means that the smaller circle is almost completely in the larger circle, and the top left of the bottom left means that the smaller circle is only barely able to cover that larger circle. Is that a correct translation of the two visuals?
I believe so. I believe the kind of top right shows us we're avoiding all contrails that we have, so our recall is very good. As we move down the chart, our precision's getting worse because we're doing more and more maneuvers that we didn't need to do. I just wanted to add here that you don't actually have to do a lot better than random chance to make contrail avoidance worthwhile. Because the numbers are actually slightly in your favor. Marc explained earlier that only about 5% of airspace forms contrails. And so the odds of doing a maneuver that then accidentally causes a contrail that you wouldn't have are actually roughly 5%, that they're relatively low. And so you don't actually have to beat the odds by very much for this to move in your favor. So we don't have to have the world's best prediction systems in order to make contrail avoidance worthwhile.
Thanks. Clear. Before we move on, is there any questions about these graphs, this visualization of uncertainty?
I would just like to make a statement in terms of uncertainty. There's one area where we have almost no uncertainty, and that's the extra fuel burn and the extra cost. Because we as flight planners, that's our daily business to predict the fuel burn very precisely. So if we calculate an optimal flight plan and a contrail avoidance flight plan, the difference that we calculate is more or less precise. So there's no uncertainty almost no uncertainty involved in the extra fuel, and that's at least one area where we can be certain in the end.
I think Raymond makes a good point, and I think it's worth expanding on. So I think the calculation of additional fuel burn on flight planning is very accurate. Obviously there's always a tiny uncertainty in everything. Scientific uncertainty applies to all numbers, but it's negligible in that instance. I think there are two things to pick on, which is we have an inherent bias from climate scientists to refer back to CO2, and so numbers that are given as, say, CO2 equivalent forget the fact that what we really should be comparing is the impact on temperature of contrails and the impact of temperature of CO2. And there is a significant uncertainty as to the impact of temperature due to CO2. It's not as large as the uncertainty as the impact of contrails, but it's not insignificant. So there is actually, when we compare the two, we often make this unfair comparison where we have this big uncertainty for the contrails, but we apply no uncertainty to CO2 warming, because that actually is also uncertain. The other is that the fuel burn penalty we can accurately calculate is versus a counterfactual, which is exactly what we were talking about earlier in the Flight Keys presentation, of either versus the perfect minimum fuel burn flight or versus a minimum cost flight. One thing that's worth noting here is the variation between planned and actual is normally much more significant than the variation due to contrails. And so to an extent, we beat ourselves up about fuel burn penalties because it's versus some hypothetical perfect world that actually doesn't exist. And if we were to implement contrail avoidance and try to measure the contrail fuel burn penalty purely by observational data, I think we would find it was actually very difficult to pick out the fuel burn penalty due to contrail maneuvers because all the other operational effects would outweigh it.
Thanks. Okay, we're going to have a few more questions later on, so keep them. I want to go into looking ahead and saying, okay, these are the uncertainties, but how do we improve them? One idea or even strategy that has come up already today, and we've heard a lot, is to do more living labs, live trials, and that would then decrease the uncertainty. But maybe Marc or Paul, you can explain how that would work. So why would doing a trial, if it's just a few flights or a few hundred or 1,000 flights, why does that improve the entire understanding of certainty in this space?
So most good scientists will tell you that you can only learn by doing, right? You actually, by definition, can't learn by doing nothing. And so by starting to monitor contrails, by starting to actually do some of the trials that people are already doing, and the more and more we do that, the more feedback loop we have between verifying what's really happened and improving prediction models. So if you want to improve prediction models, use prediction models, right? We kind of know most of the things that we do and use get better through doing and using them. So that it's a kind of very natural feedback cycle. It's a very strange pushback I sometimes occasionally see from some industry players to say, well, the uncertainty is very high, therefore we shouldn't act, and actually uncertainty being high means you actually must take action to deal with that uncertainty.
Marc?
Yeah, I mean, Paul alluded to the sort of medical analogy here, right? And you would never deploy a medicine without going through trials. You need to go through trials to understand what those unintended consequences are that you don't know fully without actually doing it and deploying it, and to work out all of the potential ways in which there could be difficulties that need to be overcome. And so you could look at it in that respect, right? So you develop a series of trials that build up confidence at each stage, and at each stage you have the ability to say, no, this isn't working, or this isn't right. There's problems. So I think that is quite a useful analogy to the medical profession that Paul introduced earlier on. You learn by doing, and you improve iteratively at that point. And so that doesn't mean that there only needs to be one trial, because there needs to be multiple trials. Mm-hmm. There needs to be trials in different airspaces, led by different people. Mm-hmm. The solution in one airspace may not be the solution in another airspace, because there are differences in the way that they're set up. I would say we need a big push on observations. So using the best available observations that we have today, so satellites, satellite imagery, ground-based imagery, we're doing work to combine those. But the more observations we have, the better we can understand whether our prediction would have been accurate or not. And with satellite imagery, we can't see a contrail formed, but we can maybe see it after 10 or 20 minutes. If we have high resolution imagery, that's something that could improve.
Is that something, maybe that you'd like to add to, Sebnem?
I would like to add operational feasibility as well, because I mean, at the end of the day, with those predictions, we are asking the airlines flight planners to reroute to flights. So with these trials, we also have access to, okay, is it operational feasible? What are the challenges? Because this is the journey for the whole, like the entire ecosystem. So it's the airlines, flight planners, also the airspace managers. So the trials also inform us for those strategies.
That's what we described as engineering uncertainties in a way. And I think that also the trials that Cetavia did, the largest error bar was there, the fact that dispatch, for example, wouldn't do it. And that's maybe an engineering side to the uncertainties. Okay, then on the data inputs and the uncertainties there, and the fact that there's maybe different sources for this data. Marc, you noted specifically weather data as one. Is that something that, when you're operationalizing this, you're trying to reduce, or how do you work with dealing with that and dealing with the different sources? Yeah,
so I think at some point we'll come to the single source of truth, but I don't think we are there yet. So how we are thinking about this is so this year, if we can, we should land on speaking at the same language and having a set of benchmarks that how we assess the models, how we evaluate everything, so that we have the same language in the industry. And then we let the innovation be there still, right? So we would like to enable that too. But having the same language and defining the set of benchmarks, how we assess everything, is key to land this year.
Okay, clear. Any other comments there?
Well, in terms of weather, there's always going to be, even if there's one weather forecast provided, there will be a probabilistic forecast that they produce. So they don't. We can't.
One weather source has one data source has multiple predictions.
Yeah. So and various forecasters will produce an ensemble as well. So different realities of what potentially could happen in the future. It's impossible to predict the future precisely, right? So how do we can account for that uncertainty in a statistical probabilistic way in terms of contrail forecasting. So it's just a sort of, we'll never reduce the uncertainties to zero. There will always be uncertainty, so it needs to be dealt with.
How do we deal with that? Okay. That's a good bridge to the next question, which is on kind of communicating that. So you're saying you have to be open about the fact that there's always some degree of uncertainty. And it's something that I think, Carlos, you work with it at TNE quite a bit on. How do you communicate with specifically airlines as the elephant in the room to be able to deviate flights? How do you communicate with them on uncertainty? What's the dynamic?
Yeah, well, first, I had never heard in my life the word uncertainty as many times as in the last couple of years working.
Well, the panel was on uncertainty, so I couldn't help it.
Yeah. So, but actually, first thing is that I'd like to thank Marc and Paul and Sebnem for kind of framing the uncertainties, because that's step number one. If everything is uncertain, then we're miscommunicating. So I think that's...
You need definitions and...
Yeah, exactly. So that's really important. And I think one message for airlines maybe, so I don't have an airline entity in front of me. I have a few individuals from a few airlines who I think are already quite excited about this. So what I would tell the airline people in this room is spread the virus. We know the topic in and out is a bit of a complex topic, but there are many things we do know already. We need to keep reminding ourselves of the potential of not reducing emissions, but actually reducing climate warming at a relatively low cost, as we'll see later. So I'd say that if we need to communicate more and more, the people who are here in the room, with more people within the industry, be it airlines or ATC or manufacturers, so that we get this room with more people, filled with more people next year. Because today we have a few people from a few companies. If we get this virus spread, that's really important because the opportunity is there. And one thing as well is that we need to unite on the things that we know. And we need to have a few key messages, because not dumbing down, but kind of simplifying the message enough is essential for policymakers. And if we have different views, different voices, highlighting uncertainties and so on, it may be very difficult, for example, to get the support for large-scale trials that we're talking about.
Great, thanks. And then my final question before we go to the room is on air traffic controllers, on kind of looking at it from the perspective not only of airlines. You've been saying we need to speak to airlines, we need to talk to them about uncertainty, communicate with them about what is certain and what we can say. How would you approach that same conversation to air traffic controllers? First to you, but then also I'm curious to Sebnem, because you're working with some of them as well.
Yeah. Well, we're starting to have conversations with air traffic controllers on this topic. And the ones who are looking at this, they're also pretty excited. Okay. Because they see that they're an integral part of a solution that can significantly mitigate the climate impact of aviation. And they're ready to live up to the task. Of course, they want to be heard, they want to be integrated in the processes. But when it comes to dealing with this on an operational basis, they deal with uncertainties on a day-to-day, with weather forecasts, with kind of taking into account the sudden closure of an airspace due to military maneuvers. So this is something they can certainly deal with. It's just integrating one more constraint into what they're already doing.
Right. Practically, is that the same when you work?
Yeah, I agree. So what I wanted to say, like we said, we are at a stage where we are moving from like pure research to operations. And this is the whole ecosystem. And so it includes airline flight planners and the air traffic management. So I think we did a good job on the airlines trial. So that was the key piece. And we'll see more on the flight planners as well. So the one that we would like to work more is the ANSP's air traffic managers. And we will be working together with MUAC Eurocontrol this year. To see what contrail avoidance means, although they're dealing with uncertainty every day, but what it means for the airspace operations and the capacity. And also, like, if you think about the whole ecosystem, everyone needs to be on the same page about the information, right? So, like we were discussing yesterday, like if an airline would like to deviate from the flight path, then air traffic controllers should have the same information that it's for avoiding the contrail, so then it's a smoother operation. But we'll explore that this year very soon.
Great, thanks. Okay, now it's your chance to ask a few questions. First here in the front, and then I see also at the back another one after that.
Hi there. I just wanted to mention there's really more statistics than you mentioned, Paul. There's just as important is the statistics that you need to have on the no contrail zones, and a lot of attention has been paid to predicting contrails correctly, and as Adam mentioned, you also have to get the other end of it right. So you have to make a double prediction. You have to make a prediction to get the aircraft moved away, and then you have to get it into the right airspace on the other side. So that does complicate the numbers a lot, actually, getting both predictions correct. So I just wanted to add that to the mix. It's even more work to convince people of both sides.
Is
Yeah,
that
agreed. Yeah, very much.
agreed? Good. Is it response to this point? Okay, then let's do this first, and then I'll go to Jan.
Just a very quick one. What we are doing here is not a binary thing. It's not contrail, no contrail. We avoid something or not. We are doing cost-based avoidance, so it's a very continuous cost function that we use. So we can easily adapt to uncertainties as well here. That's something important to understand, because this hit rate seems to indicate that we either hit it or we don't hit it. There's a big gray zone in between, and it can go either direction. It can be more or less. So that's also something we need to consider.
Yeah, and that's, I think, part of that was taken when you showed the blocks, the battleship analogy, with some predictions being light gray. But good. Yes, I think to the back, there was a hand there, and then here.
Hi, good morning. My name is Jan. I work for DHL, so one of the airlines trying to spread the virus, although that's a bit of a difficult analogy these days. I think this was very interesting. Thank you for your presentations. The question that I had, because you talked a lot about the sort of the entire system uncertainty, I was wondering if in your models you actually are able to have that uncertainty a bit more granular. So, for example, I would imagine that if you have a clear sky, no natural cloud cover, no interfering other aircraft in the airspace, it's quite certain what you do, and you pretty much know what's going to happen. Where as opposed to a very busy airspace, natural cloud cover, lots of other contrails interfering with your contrails, you're probably going to say, well, I don't really know what's going to happen here. So is that so? And if it is the case, do you take that into account in these calculations?
I think this comes into the kind of known unknowns and the unknown unknowns, and the unknown unknowns are the reason, as Christoph mentioned earlier, that we have to do some of these larger trials where we start to see the knock-on effects, for instance, in the more congested airspaces, how many more other aircraft that might not have even been in a contrail-forming region we have to move out of the way. There are model methods for effectively including unknown unknowns, typically including things like black swans into planning, which is often relying on evidence from other areas. It turns out that is often not a bad predictor. So, for instance, looking at disruptions due to turbulence and looking at the consequences for moving around turbulence is a good first estimate as to what the impact is. But this is, to me, one of the largest uncertainties we really need to deal with at the moment is around that congestion space and the impact on ATC. And as I say, we will only learn more about that by trying some of that, both synthetically and in practice. I mean, thankfully for air traffic control, obviously you can do synthetic measurements where we pretend to route flights as opposed to crashing them into each other.
Thanks. Yeah. Anyone else like to respond to that, including that in models? Or no? Good. Very relevant question, ties into ATC as well, and congestion. So good to have them maybe join us as well next time. I saw a question here first, and then going.
Yeah, just a quick one. Niels Buus Christensen from Institute of Transport Economics in Oslo. As I understood it, uncertainties on, let's say, the weather forecast was one of the big issues. We hear a lot about artificial intelligence is going to improve these forecasts radically. Is that something that you rely on?
I think maybe I'll pass over to Google, who have some expertise in AI. But I think the challenge is data. All right, so with any AI system, you need a lot of data to train a model, which you can improve the design of that model, but ultimately you need lots and lots of data. Unfortunately, we don't have lots and lots of data yet, but there is some humidity data. There are contrail observations data as well. So that contrail observations of where contrails are forming gives you information, and that's valuable information.
Yeah, and then I mean I can add to that, like the AI increases our capability to analyze that data, right? So even if we have huge data sets, we didn't have the capability to analyze that. So this is what we are using in the model for the time being. We are giving like all the data sets that we have in the world so that the AI help us to analyze it, to evaluate it. So in that regard, yes, when more data is available, and also we are adding the satellite imagery data as well in US and now in Europe. So it will help improve the weather forecasts. Yeah.
Thanks.
Hi. Hi, my name is Paul. Marc, you mentioned just before something about uncertainties also on the registration of the CO2 emissions from the aviation sector. Are you referring to the study from April last year from a Norwegian group of scientists showing that the registrations to the UN system is actually inaccurate because third world registrations of CO2 emissions from aviation is not really calculated, but it is assumed somehow. Is it such kind of studies you are referring to, or what is it?
So our CO2 projections in models we can do in a number of ways, and actually it does turn out it's actually quite a difficult problem working out how much CO2 aviation burns in a year globally. Thankfully, we can approach it in a number of different ways. One is to look at all the flights and look at the ADS-B data and use models that people like Flight Keys and others use to predict the fuel burn of those aircraft. Others is a very crude method, which is to just look at how much jet fuel is sold in the world, because jet fuel is pretty much exclusively used in aviation, and we can kind of marry up these estimates. And yeah, there are always some data gaps, but kind of broad speaking, we can put those data pieces together.
I see 3 more questions. Okay. Can we do that?
We can do 3 more
okay.
questions, yes.
Dennis, and then...
Who is it?
No, you're first Dennis, and then... Oh, no. Ready?
Sorry.
Too close. Thank you, and thank you both to Professor Hodgson and also Carlos for kind of exemplifying the uncertainty, rather the trade-off uncertainty for those of us who are more STEM challenged, as it were. I think we can all relate to a Venn diagram and certainly more to a heat map. What I want to ask, is this one is specifically for Professor Hodgson, is I remember you mentioning the need for airspace living labs, as you call them. And I was wondering, how do you envisage that? What does it really look like? Is it something along the lines of what MUAC was doing? Is it an expanded version of that? Is it a different principle of operation altogether?
I think I might defer to later, because otherwise I'm going to repeat myself later, because we have a talk on that topic this afternoon that I think be great.
It's going to be a big part of the presentation at 3:55.
So be there.
Be there.
Quick question over there, and then did you have a question for me? Yeah? Okay.
Thank you very much. Marc, you mentioned this morning that you said SAFs are not going to remove contrails, and now we just heard that it will provide a significant reduction. Could you perhaps share some more insights as to what are the uncertainties in those numbers?
Yeah, so Christiana showed some really world-leading measurements on the effect of SAF on aircraft emissions at cruise level, and it does show a reduction in the number of particles emitted by the aircraft engine, non-volatile particles, and a reduction in the ice crystal number. So it changes the contrail properties. I think what we are still, there's a gap in understanding how that propagates through to the contrail lifetime and having observations of that over a longer period of time. So the measurements behind an aircraft tell us something. Our models tell us something. We have to understand also from observations what is the effect on the contrail lifetime. I think the other uncertainty there is that obviously you need higher blends of SAF to achieve the larger reductions in particles, and so there is that's a different type of uncertainty, right, as to how far SAF is going to be taken up, how quickly, and does it scale, etc. And so if you're kind of just thinking, well, okay, mandates say that there'll be a few percent of SAF, say by 2030, that change in the contrails is going to be pretty small if you have a low blend ratio on all sides. Yeah, I think that so hydrotreated fuels potentially have a similar benefit, but don't forget that if you have hydrotreated fuels, you need to put energy into the process of making the fuel, so there's CO2 associated with hydrotreating the fuel.
Good. I think that's it for the... Yeah, I said 3, so one more question, and then we're finished. Then we have some closing remarks.
Yeah, thank you for that, for all of the great points. I'm curious to check on the point that you just made about SAF and the SAF mandate by 2030. So the SAF mandate, I think, in its current state is about 2% on average. Now, when we do contrail calculation, we assume a specific amount of SAF in a given flight. Now, talking about uncertainty, if we say 2% on average, we actually just have no idea how much SAF is going to be in each specific flight. How do you see that acting out on the uncertainty? I mean, clearly it increases the uncertainty, but in a practical way. How do you see that interaction going to pan out in the future?
I'm not only we don't know the blend ratio on a specific flight, but there could be no SAF on that flight, and the SAF is somewhere else in the world. Yeah, observations are critical, right? To understand the effect of SAF. But I think if we're talking about a few percentage points of SAF, it'll be very difficult to observe a difference compared to what it would have been. I mean, obviously, then you get into problems of having a counterfactual, but I think, yeah, I stand by the point that SAFs aren't going to eliminate contrails, certainly not in the near future at low blend ratios. And so we need to just establish that as something that we know. Obviously, they might be helpful, but at current projected mandates and things, we're still going to have contrails.
I think very quickly on this, I think there's a couple of important points. So firstly is that it would be great news if SAFs and hydrotreated fuels indeed reduce contrails. That's a win as a start. But 50% of a very big number is still a very big number. So if we want to get to net zero, we will still have to do contrail avoidance on top of hydrotreated fuels or otherwise. So we kind of need to do that. And that kind of leads to my second point, which is when you're in an emergency, you throw everything you have at it, right? There is a kind of inherent bias of the kind of perfect being the enemy of the good in lots of us, which is kind of like, oh, well, the SAFs will only maybe like this much difference, so we shouldn't bother with that. And contrail avoidance is not perfect, so we shouldn't bother with that either. And when you have a big problem, you actually tend to need to tackle it through multiple approaches.
Yeah. And maybe there is, I think, research coming from your colleague, Roger Teo, and some others on dedicated SAF supply simulations. So really assessing what that would look like if you would have specific high blends to specific airports or specific to the night instead of the day or specific season. So that's something that is being researched and potentially something to look into. Okay, can we give a one sentence closing per panel member on kind of what we discussed and what you'd like to be the key takeaway from at least this first morning?
I'll paraphrase Paul and say we learn by doing.
Okay, you took Paul's final sentence.
Different sentence. Yeah, I think going back to the perfect being at the end of the good, that businesses and governments fundamentally deal with uncertainty in all decisions they make. I think it's interesting that Carlos earlier said that there's this kind of attraction to uncertainty with contrails. Most of the decisions we make in sustainability and most decisions all businesses make have risk, all investments have risk. We're actually very used to dealing with risk. This is not a fundamental blocker to action.
Thanks.
So building on that, contrail avoidance is complex, but aviation is really good at complex. Like we have thousands of planes literally flying very high, very fast in the atmosphere at any given time. We take it for granted, but we need to be aware that that's not something which comes like that. So I'm really convinced. I mean, I'm infected by the virus, so I'm a bit biased, but I'm really optimistic that we can crack this.
Thanks, Carlos.
So I think like all of us in this room are working towards the same goal, how we can make it possible. So I think each party is bringing their own expertise, like research, technology. What I would like to say as a technology company, we are ready to provide our resources towards that goal to the industry.
Great. Okay, big round of applause for the panel. Woo!